let's now talk about what's called the complement of a set. First, we were talking about what elements belong to a set, but the complement of a set is actually looking at what does not belong to a set. So in complex problem-solving situations, sometimes even in our day-to-day activities, we want to be able to identify all the elements that we're considering. So, for example, if you wanted to figure out all the different possible area codes, well, here you would only consider 3-digit numbers that do not start with 0. Everything else is a potential area code. So the set of all the elements that you're considering would be the universal set. We can use the letter U anytime that we are trying to identify this idea of a universal set of whatever it is that we're considering. So the complement of a set would be anything that's in the universal set, but it's not in the set that we have identified. So for example, if I wanted to look at area codes of Virginia as being my set A, then I would list the numbers 540, 804, 434, 757. I'm sure there's some other ones, but that's all I can think of right now. Those would all be elements of the set A, area codes for Virginia. The complement of that set would be all of the other numbers. So for example, 678, I know that one is not in Virginia because that one's down in Georgia. 770, that's another one that's down in Georgia. So that would be a number in the complement. So you have your set that contains what you're looking at, and then you have your complement, which is everything that is one of the items that you're considering, but you have not placed it into the set that you're talking about. I know that's a little confusing, so let's look at an example. If our universal set was the counting numbers from 1 to 10, and we identified a subset 2, 3, 5, and 7. The complement of that set S would be everything that's in the universal set, but not in S. So you would end up with the list 1, 4, 6, 8, 9, and 10. That would be the complement. One little note to make here, the complement of the universal set is the empty set, and the complement of the empty set is the universal set. So you can think of the universal set as everything, and the empty set as nothing. I used the word subset a moment ago, and when I'm talking about a subset, I'm just talking about a set that I have pulled from a bigger set. So the definition of a subset, here we could say set A is a subset of set B. Now don't worry about these letters, it's just noting that we are making some sort of a set. If we have that A and then the little U on its side with a bar underneath it, that shows that it is a subset. Something that is a subset means that every element of the subset is an element of that larger set. It has to be because your subset is being pulled from that larger set. So for example, if we had the set A, 2, B, 4, C, and 6, that would be a subset of the list A, B, C, D, 1, 2, 3, 4, 5, 6, because every element of that smaller subset came from the larger set. Now example 2, where we had A, 2, B, 7, C, and 8, would not be considered a subset because the elements 7 and 8 were not in the larger set. Now, for example 3, you see that the two sets are themselves 2, 3, 5, 7, 11, and 2, 3, 5, 7, 11. This would be considered a subset because every set is actually a subset of itself. So you don't have to have anything different. You can have everything exactly the same and still be a subset. The empty set is actually always a subset of every single set. And then one more kind of mathematical thing, and I don't want you to get too overwhelmed with all of these mathematical definitions. We just have to spend a little time looking at set theory so that we can understand the foundations of some of our logic that we're going to do later on in this class. But when we have what's called a proper subset, where it doesn't have that little line underneath it, that means that every element of A did come from B, but they were never exactly the same. So that example 3, where they were the same sets, they were a subset of each other, but not a proper subset, because a proper subset, there has to be at least one element in the bigger set that was not in the subset. So let's look at a few examples applying the definitions of these subsets. We have 2, 6, 9. Is that a subset of 2, 4, 6, 8, and 10? Well, the answer is no, because 9 shows up on the left, but it doesn't show up on the right, so that would not be a subset. Then for B, 1, 3, 5, 7 is a subset of 3, 5, 1, 7, even though they're in a different order. They all have the same, or all of the elements in the left set are in the right set. C, that's true because the empty set is always a subset of every set. And the only problem with D is, yes, 3 does show up in the list, 1, 3, 5, 7, and 9. However, 3 is not a set because it doesn't have the little brackets around it. So D could be fixed by putting the little curly brackets around it, but right now that 3 is not a set, it's just an element.